Yeah, that was suggested earlier. We should have a sort of a shuffle talk thing where we give each other's talks and see what we have to say about them. I'm going to talk about possible ways to produce the S-stars in the galactic center. I'm going to talk about a couple of ideas, not all the possible ways of making them. Just to remind everyone, we've seen this picture before. This is an infrared image, so it's important to remind everyone that the galactic center is buried. It's a really hard place to look at. There's lots of gas and dust between us and it, so you have to look in the infrared. This is an infrared image. That's 6 light months across there. Blame people at Max Planck for the units. Important point here, nice big bright red things around the center, not many bright red things in the very center. The S-stars, which I'm going to talk about, are right in the middle here. We saw earlier in the week a nice movie of the S-stars. I don't have that, I'm afraid, to show you. But here's the S-stars. This is now 20 light days. So these objects are very, very close in to the galactic center. So they're blue objects. If you believe that they are what they look like, they are main sequence stars of masses somewhere between 5 and 10, 15 solar masses, that order. Okay, so to keep you all awake, there are 2 ideas in this talk. See if you can spot any of them. Okay, there's at least 2. Okay, and I will also suggest at the end that 1 plus 2 is less than 2.35. So to confuse anyone who comes in late, I'm going to write that on here. 1 plus 2, and we'll come back to that at the end. There's actually potentially an interesting point that only occurred to me this week. So maybe it's interesting, we'll see. Is
that a statement about Lisa's budget?
Well, maybe, yes. We can all decide. You can all decide what this could mean, and we'll all go around the room and have people. Mark will tell me what this means by the end of the talk, I'm sure. Okay, so first idea, see? So if you're not paying attention, this is the first one. Okay, the first idea is really a variation on a theme we've heard before from Cole Miller and Mark Freitag's idea with others, that you can make a capture by throwing in a binary, tidally breaking up a binary, keeping one of the stars in a tight orbit. So the idea here, slight variation, is rather than throwing binaries individually, one at a time, I take a group of stars, a cluster containing some binaries, and throw it right at the black hole. Okay? So the idea here is that several binaries can be thrown at the black hole in a single event if all the binaries are contained inside a stellar cluster. Okay, this is not an absolutely crazy idea. Okay, and I'll explain why it's not an absolutely crazy idea briefly today. The point is the following, is that we can produce clusters in the galactic center. We know we produce stellar clusters in the center of the galaxy because we see them. There's a thing called the Arches cluster and quintuplet cluster. They are young stellar clusters. They're actually not right in the middle. They're about 10 or 20 parsecs away. But they're very young objects. They must have formed essentially where they are seen today. Okay? So they're rather like, in a loose sense, young globular clusters. They're actually a little bit less massive. They're about 10 million years old each, or less. And they contain lots, therefore, of massive stars. So if I took an Arches cluster, I plucked out the Arches cluster from 20 parsecs and threw it right at the black hole, the bottom line is that any stars within 0.0 few parsecs of the middle of the cluster, that sort of cylinder, would all pass close enough to the black hole that if they were 2 massive stars in a binary of separation an AU or so, they'd get split up. How many stars in the Arches are in that cylinder? It's about a few hundred. So if I take the Arches cluster, threw it at the black hole, a few hundred stars would pass close to the black hole. Doesn't mean we make a few hundred S stars, because not all the stars are in binaries of the right separations, but there's a reasonable chance that you might capture 10 or 20 stars. That's the idea. Okay, and that's what I've just said. So binaries in the cluster pass close enough to broken up, leaving some on very tight orbits. And then the question is, are these the S stars? You could have reasonably asked me, why do I care if the binaries go in one event or just one at a time? That's a fair question. Important points that are here in a sense astrophysically is if we have one unusual event, it can affect the rates, right? If I have 20 individual events, then I've got a much better handle on the statistics of the rate that I need. If I've just had one unusual event, I could have just been lucky. I could be 1% lucky, and the event rate could actually be lower than we think. So it's important to understand this. And I should mention this is work with a say former PhD student of mine. It sounds awful, but he just finished. Johan Dischler working with me, and Dougal McKay and Mark Wilkinson in Cambridge. Okay, so again, just to make it clear, this is a sort of cartoon of a binary being split up by a black hole. So a binary comes down, gets very close to the black hole, gets tidally broken up, we kick off a star. People talked about it earlier, these high velocity stars which we have seen, which we've seen them way up in southern Germany, and you capture a star. Important point here again is this distance here is about 100 times the size of the binary, so it's about 100 AU, what was that, few 10 to the 4 solar radii and whatever the units you want. Important point here is gravitational focusing. This distance here is enormously bigger than this distance here. This distance is sort of 0.0 few parsecs. So it's not a crazy thing. I'm not scooping out a few stars within the inner few hundred AU in a cluster. It's a cylinder of stars with a radius of 0.0 few parsecs. And that's how we get a few hundred. So again, our idea is you throw a cluster containing some binaries at the black hole. I'm just going to show you a few snapshots with a sort of semi-funny story. So what we have here, we actually did n-body simulations. We used Sphero-Cess n-body code, built a stellar cluster, and just threw it at a black hole. Okay? If anyone's ever worked with Sphero-Cess codes, you know it's not quite trivial because they never work properly. But we got it to work, or Johann Dischler got it to work for his thesis. Here's a stellar cluster. I'm not sure how clear it is on here, but the distance is here. There's the center, there's the black hole. This distance here is 30 parsecs. Okay? So we build a cluster 10, 20, 30 parsecs away, throw it at the black hole. Okay, that's sort of time t equals 0 in a sense. There's the black hole. Here's later, here's a little bit later, much later. When we first made this, I have to say actually, faith in PhD students, he showed a video, Johann made a video, and I hadn't really thought about it. So the cluster comes in, the black hole's there, the cluster comes in, it does this, it bounces off. And my first reaction was, okay, but of course it's correct because all the stars are getting so close to the black hole that all of them are being deflected by almost 180 degrees. Okay? In this case here, our velocity was a bit different, so they're not quite 180 degrees, but this sort of crescent here is stars coming zooming around and heading off here, or zooming around and heading off here. So that's why there's more stars here. They're all flying away from the black hole as they've been deflected by 100 and something degrees, close to 180 degrees. An important point here I should make before anyone asks me is you can't see this, you don't see it in the galactic center, but you couldn't anyway, because this distance here is sufficiently large, it's 30 parsecs, so even if you had this, you would be lost amongst all the other stars. Okay, so the number of stars contributing to the population at 30 parsecs from my one stellar cluster is small, so you don't see the structure. So anyway, zooming in, do we actually capture any stars? The answer is yes. That is not surprising, because really just doing the n-body runs, we really show the idea works. Though we don't see one idea that might have worked, which I'll come to in a minute, so it was worth doing the n-body runs. Okay, so what I have here is eccentricity in a crazy unit here, but basically these things down here are very eccentric and up here is slightly less eccentric. This is the same major axis in parsecs, 10 to the minus 2, 10 to the minus 1, 1, 10 to the minus 3. The x's here are the S stars, and there's various different runs here. I won't go into the different runs, there were different distances and velocities, but the bottom line is we're making objects here, we're capturing stars at the right sorts of distances. This isn't very surprising because we put binaries in that we know would be split up, but we are actually seeing it working in the n-body code, which is good. The other thing we did not see was something which we thought we might see, which we've discussed before with some people, is I wondered if, because we have so many stars around the black hole, that you might capture one by a sort of three-body binary process. So just to remind everyone what I mean by that is the following. If I have three independent objects, initially all unbound to each other, they all come in close together. One of them can carry off the energy, leaving two bound. This can be an important way to make binaries in stellar clusters if there are no primordial binaries. So one might wonder if you could capture a single star this way by having loads of stars around at a certain time. We don't see that. Perhaps it's not so surprising because, in fact, at any given time, there's not much around the black hole. Because if you're one side of a cluster or the other side of the cluster, as you go into the black hole, you're thousands of years away from each other. So actually, at the black hole, you're way away. And it was worth checking that. We didn't see any of these captured stars. None of them were single stars. All of these captured stars were initially in binaries. So we're breaking up, every of these is a broken up binary, in other words. So very quickly, then, summarizing idea number one is basically that we can throw a cluster in. It'll leave several stars on tight orbits. The masses are quite high because the binaries in the middle of a cluster tend to contain more massive stars. So it's interesting that they would contain quite massive stars. And the big question mark over this whole thing, really, is what is the probability of doing this? It's not as crazy as it sounds, because A, we know that clusters are made in the galactic center because of the arches and quintupla. I think Tal mentioned yesterday that we know observationally there's molecular gas in the galactic center. And if you just assume that the gas is in normal molecular clouds, as in elsewhere, you get a collision between two giant molecular clouds perhaps every million years or so in the central region. So it's not utterly crazy. We don't really know what the distribution of the gas is. We don't know the distribution function of the cloud orbits. Mea culpa on that. But if you're fairly conservative and reasonable, you can sort of get a probability that you get a cluster thrown inwards, perhaps 0.0 few as the probability that's happened in the last 10 million years. So the idea I should explain, perhaps I didn't explain clearly, is to make a stellar cluster. I have a gas cloud moving and encounters another gas cloud. They smack into each other. They compress the gas. Stars form out of the compressed gas, and those stars move with the net momentum. So if I have a cloud and an anti-cloud come in with equal and opposite velocities or very similar speeds, then the stars fall in at relatively low speed. And that's the idea. Okay, second idea then, very quickly, is completely different. Okay, it's something we did a while ago with Andrew King in 2005, and it's a completely different thing. And we'll relate the two with this at the end. So the idea is the following. Nothing at all to do with the clusters. If I take a red giant, a big red giant, so red giants, to remind everyone, the sun is a main sequence star. It will evolve off the main sequence. The envelope will expand to be perhaps the order of 1 AU, a thing called a red giant, a big red thing. So we scatter in red giants towards the black hole, and we tidally shred them. There is an interesting coincidence which got us thinking about this, and it's the following. If you look at the S-star orbits, the minimum distances of the S-star orbits, as we've seen already, is perhaps 100 AU or so, right? So we split up a binary of 1 AU to make an S-star orbit. In the same way, I could throw in a star that's also 1 AU across, a red giant, and if I could tidally shred that and dissipate enough energy, and that's the question really, then I could potentially capture the core of the red giant in a similar tight S-star orbit. Now, red giants are funny things, okay? If I have a red giant and I smack into it with something, like a black hole in a collision, and perhaps remove half of the stellar envelope, you might think, well, that would look a funny object. In fact, if I came back later, even if I removed half of the red giant's envelope, what would happen is the remaining envelope would puff up over a thermal time scale. If I came back later, it would look almost identical. This is why a 1 and a 2 solar mass red giant look the same. If you're familiar with a Hertzsprung-Russell diagram, a 1 and a 2 solar mass red giant occupy the same place. They have the same radius, luminosity, and surface temperatures are very similar because a red giant doesn't really care about its envelope mass. But if I can really, really clobber my red giant, remove almost all of the envelope, then I'm left with a little bit of gas around the core of the red giant. So I should explain for those who are not familiar, to remind everyone, a red giant has a core. It's going to become a white dwarf in most cases, or perhaps explode and make a neutron star and a more massive star. Nuclear burning is going on essentially inside the core to give the energy. So if I have a very low mass envelope left around the core, then the object looks blue. That makes sense, right? Because there's less atmosphere. I'm cooling as I go further out in the atmosphere, so if I have a smaller, shallower atmosphere, the surface temperature would be hotter. That makes sense? So I can take a red giant and make it blue. But, crucially, if I've done this, the luminosity may not be so different because the luminosity is coming from the stuff in the core, the nuclear burning in the core. So I can take a red giant of a certain luminosity, remove all the envelope, and make a blue object of similar luminosity. That's the idea. And perhaps these are the S-stars. So let me just try and show you that graphically. This is what's called a Hertzsprung-Russell diagram. So it's temperature here, luminosity here. For those who perhaps don't see these very often, I should warn you something very important fact about the Hertzsprung-Russell diagram is that hot is on the left and cold is on the right, something which pedagogically I neglect to explain in this plot. I guess you can count the tick marks. Okay, cold stuff is here. Red giants are red, so they're cold, but they're big, so they're luminous. Okay, this is log luminosity here in solar units. So these things are very bright objects. I should explain something that's very important about the galactic center again. I mentioned you observe the galactic center in infrared. That's a very strong selection effect. It means you see red things or very bright blue things. Okay? And what that is, I forget the exact numbers, but these are lines of constant K magnitude, one of these crazy astronomy units. But what it means for us here is that basically I can see anything above a line that's roughly here. So I can see red giants easily, and I can see very massive main sequence stars over here, but not the sun or 2 solar mass main sequence stars, because they're below this line. Okay? So the idea is I take these red giants here, I shred them, and I move them here. Okay? So roughly keeping the same luminosity, but you're losing all the envelope and you're making them look very blue. Thanks. Okay, I'll zoom through that because I already mentioned it. So the bottom line with this is that the size of the orbits of the S-stars show us that if I do scatter in a red giant into the black hole and have that minimum distance of about 100 AU, I will tidally disrupt the star, okay? In the same way that we broke up the binary, essentially, the tidal field of the black hole is enough to pull on the envelope and do a lot of damage to the envelope. That's not disputed by anyone, I would say, almost. I mean, it's quite clear if you get close enough, you will pull apart the star. The question is, though, is the following, and it's a rather morbid analogy maybe, and it's perhaps a dangerous one, but if you're driving your car, I don't have a car, so I can say this. If I'm driving my car and the car stops suddenly, and I don't have my seatbelt on, I go through the windshield, right? So the question is, does my stellar core in my red giant keep going, or if I completely destroy the envelope, does it dissipate enough energy to be captured? And we do have to dissipate an awful lot of energy, right? Because we're going from infinity to leaving ourselves orbiting in a very tight orbit around a very massive object. And this energy in ergs, if that's useful, perhaps it isn't for people here, but 10 to the 49 ergs is a lot of energy for a star. Okay, and you can compute that trivially with the right distance here. So the question is the following: how does that energy compare to the energy available, in a sense, in my red giant envelope? So here's my red giant envelope, and just think about peeling off the outer layers of the red giant envelope. So this is not a detailed hydrodynamical calculation I'm doing here. I'm simply taking a static red giant model and asking the question, if I just start removing the mass from the outside inwards, how much energy do I need to do that? Okay? And it gives us some sense, at least, if it's completely crazy or not. So here I have two red giant models. So there's mass here in solar masses, 6 solar masses for one and 4 for another. And this energy, I apologize, we wanted 10 to the 49 ergs, and by some slip, I've given it here in units of 10 to the 48. Sorry about that. So 10 here is what we want. So the point of this plot is the following, is if we take, for example, the 4 solar mass red giant, this is this model here, and I start peeling inwards. So in other words, if I get to here, at 2 solar masses, I've removed 2 solar masses of the envelope, and the energy required to do that is about this much here, which is what? 1 in this unit, so 10 to the 48 ergs. So in other words, if I was only to remove the outer 2 solar masses of the envelope very efficiently, without kicking it off at ridiculously high speeds, I wouldn't dissipate enough energy. It's only 1/10 of the energy, so the thing would just go flying out again. Okay? But it's interesting to note, therefore, the following. It's sort of a chicken and egg thing, perhaps, that if I can get rid of all of the mass of the envelope, so I go in, all the way up to here, you can see the energy is increasing steeply here as a function of mass because I've reached the dense core, right? It makes sense. As I go deeper into the potential well, the energy per unit mass I have to put in is larger, right? And that's why this gets steeper here. So if I can sort of remove order 10 to the 49 ergs here, then I'm digging down into the red giant. I'm really removing essentially all of the envelope. So I'm getting down to the core and perhaps leaving a little bit of mass just above the core. Okay? That doesn't prove it happens, of course, but it proves the following, that if I take a red giant and remove enough mass to dissipate enough energy, the thing I have left really is just the core and a little bit of gas. Okay? That sort of proves in a sense. So it's not a crazy idea. And in terms of dissipation connecting to the core, the driver analogy, what's the seat belt? Well, the point is that when you actually tidally shred the red giant, it's going to be quite a complicated, messy thing. What's actually going to happen is the red giant will come in. The first thing that really happens, it gets compressed in the other direction, right? So if the floor is the plane of the orbit, there's a Z component of the gravity and actually compresses the red giant. And then it's going to stretch it. It's going to make like a sort of banana type thing. And it'll launch rarefaction waves into the fluid of the envelope. And as they get to the core, there's going to be a lot of sound waves and activity. This core is very dense here. So it's basically like a white dwarf. So if I excite modes in the core, wobbling around a little bit, it could actually contain quite a lot of energy. So it's not obvious that you can't couple the core here to what's going on as you strip the envelope. Okay, so that's where we were in 2005. There's some obvious questions about this. Okay, there's several questions, and there's a couple here I just want to mention briefly before I get onto the whiteboard. And it's the following. So you can sort of work out the rates of this, and you can see that they're perhaps reasonable, or at least worth thinking about. But there's obviously valid questions here. Is what is the lifetime of the stars after shredding, and how do they evolve? In other words, where are they on that Hertzsprung-Russell diagram? If I take a red giant, I remove most of its envelope, I bind it on these tight orbits, what does it look like, right? Because if it just turns off the core and it's very faint, I won't see it. It won't look where the S-stars are. And this work has been done, I'll direct you, because we don't spend much time now, to a paper which has now appeared with Lynette Dre, who was a postdoc working with us on this. And what she did, she actually was originally a PhD student of Chris Taut's in Cambridge, and there's a code called the STARS code, which is a STARS evolutionary code, written originally by Peter Eggleton, one of the key workers in this field. And so what Lynette has done is taken this code and basically removed a large fraction of the envelope mass and then evolved the star in the stellar evolution code. Okay. And this is just an example. I'll direct you to the Dre paper for more details. But to show you what's going on here, so this is a HR diagram again, hot on the left, luminosity increasing. Here's the regular evolutionary track of a 4 solar mass star. And it's moving up to what's called a giant branch here. And at that moment there, Lynette instantly removes 99% of the envelope. This is the envelope mass here, I should say, not the whole mass. And then the star comes over here, and the red track is a subsequent evolution in an HR diagram of that object. If you remember what the other diagram looked like, we wanted to basically take things over here and make them over here. So you see this object is sort of the good news, bad news, right? The details get complicated, but the star sort of evolves around here a bit and then moves off over here again. But you can see that it's bluer, and at least for some of the time it's rather luminous. Some of the time it wouldn't be seen, it's too faint down here, but it certainly passes through a zone here where it would look essentially like an S star, at least in this diagram.
Excuse me, the question, is there any energy input into the remaining star on the
That's a good question, actually, yes. I haven't thought of that before. The answer, therefore, is no. We haven't thought about it. That's right. So you could ask the question, for example, do I mess the core up enough to change things a lot? My guess would be over the time scale of this, I should mention this thing here evolves. It spends about, this is basically evolving on the time scale of order 1 million years. So it's really rather a long time scale. So on my guess, my gut feeling, though people should add comments, is that what we do to the core at the instant of capturing it, give it a big wobble or something, will probably not matter on this evolutionary timescale, would be my guess. But it's an interesting question to think about. I think, unfortunately, in details, the model gets complicated. What we really find from the detailed calculations is it does work, but how often it works and what you need to do to get it to work is complicated, right? Well, what mass stars do I shred and when? How far up here are they? So it could be something to think about, though if sort of hand on heart, it's probably not going to be the major route for most of the S stars. We gain a little bit, but not a lot. See, one of the problems I should have mentioned already about the S stars is this paradox of youth. Andrea Ghez at UCLA quite, is you get these young stars very close in. So this would be useful if I could make a low mass star look like a young high mass star. But our low mass stars are only a little bit lower mass than the stars they're trying to mimic. So to be clear, for example, to get a star looking like a 10 solar mass star on the main sequence, we need to shred something over here that's perhaps 6 or 7 solar masses. So we don't, in reality, gain a lot. Yes, sorry, just to be clear again. This is the envelope mass, not the whole star. Sorry, yes, that's a good point. Yeah, well, but also, of course, you've got the whole core in here, right? So you're basically going through, for the people who follow these things, this is basically go through a helium main sequence, essentially, here, right? So then we go into, so this is a pre-helium ignition red giant here, and so we go into later burning stages and getting more luminous. Yeah. Yeah, so what happens is the star comes down here, and we have essentially the helium star core. So at this point here, the red giant here, what it's got a helium, so here's the main sequence, fuse hydrogen to helium in the core. At this point here, we've got a helium core, hydrogen envelope, bear with me. Here, that helium core starts burning, so it's called a helium main sequence, essentially, because the atmosphere is very low mass. And then once I've gone beyond that, then I go through sort of later burning stages as a giant over here again. For people interested, I direct to the Dre paper. Okay, so very quickly, large red giants can be scattered and shredded. If we can capture them and lose enough of the envelope, which sort of is a consistent thing in a way, some of them will appear blue. But again, in the details of the Dre stuff, which we've just done, it really shows that the gain isn't perhaps so much. But it certainly will happen. Okay. So let me come back now. I think I'm on time still, aren't I? How are we doing? 1 minute. Perfect. Is to this point here. Okay. So what on earth is it? It's actually, I deliberately put it 2 plus 1 to confuse any late-coming relativists, you see. Okay. So 1 plus 2 is less than 2.35. Well, some of you in the audience will know what this is. And let me write on the board because it's important to try and be clear. And I will be quick. It's a small point, but I think it's an interesting one. This number might be familiar to you. 2.35 is what's called the salpeter mass function. So just to remind everyone, what that is about the mass function, the distribution of stellar masses. So I make loads of stars. What's the distribution of their masses? I've got some low mass stars, some high mass stars. And salpeter came up with the following. that the number dn dm, so that's now the stellar mass and the number having that mass, is proportional to m to the minus 2.35. This is not the unique sort of observational fit, but it's a fairly common fit. So that's my 2.35 here. My 2 plus 1 or 1 plus 2 really is a sort of combination of the 2 points of my talk, is to remember the following. If I go back to my red giant, to my HR diagram. So in point number 1, the idea number 1 was I was throwing a stellar cluster at my black hole, okay? And one of Clovis's questions, which I will now answer, could have been the following, or anyone's questions actually, but people who've thought about these enough, is, well, hang on, if I make a cluster inverted commas at 10 parsecs and throw it into the black hole, how long is it going to take to get to the black hole? Okay, so I've got my cloud-anti-cloud collision again. We're leaping back to the cluster again, sorry. Cloud-anti-cloud collision, compress the gas, make some stars. That will happen. I think that's okay. And let's assume that sometimes the velocity is sufficiently small, they're falling in towards the black hole. Depending on that velocity, of course, there's the details of the acceleration, but that time to fall in is perhaps only 1 million years or so. It's not a very long time, because we're heading straight at the black hole. That's the point of this. Okay? Now, that's two things that are very important about 1 million years. Okay? And I'm going to use my HR diagram here to try and explain, but now the things are completely different. Stars are weird, right? So a star like the sun would be our main sequence star down here, burning hydrogen to helium, and then it evolves to become a red giant. But if I looked at the sun before it was on the main sequence, it actually goes the same route, essentially, but the other way. So the sun, when it forms, a forming sun, starts out as a bigger thing up here. It's not doing what the red giant's doing. It doesn't have a helium core or anything, but it's up here, and it actually cools onto the main sequence. The time scale for that, crucially for low-mass stars, is longer than this 1 million years, right? Okay. So if I take a cluster that's really young, less than 1 million years, the only stars that are not big fluffy things, rather counterintuitively, are the more massive stars. So now let's throw my cluster again at the black hole, and all my low-mass stars are big fluffy things. Okay, they're going to, if they're in a binary, they can't be in a binary that's 1 AU if they're already 2 AU apart. And if they are single and get close to the black hole, they'll get shredded. Question, will they then capture? Answer, no, because they're not a red giant, they don't have a dense core, they're just a big fluffy thing. They'll just get messed up. Okay, so the point here, again, just to reiterate before I finish, is the idea that throw a cluster in, the only stars that are star-like are the massive ones, because the others are big fluffy things, so that was point number 2. Point 1 was the cluster coming in, and so it's less than 2.35 means that the mass function of things I'm capturing is much flatter than this. It predominantly, well, it favors the more massive stars. Thank you.
Okay, we have time for one good question.
Yeah, it's a bit of risk I take here. Okay, well, thanks for for answering the question I didn't ask. But I have another question. Could you maybe explain a bit? I'm not sure I understand this analogy with the braking car. So you gave an energetics argument, but I'm not sure I understand why all the gas suddenly stops at a tidal disruption. Why doesn't it, for example, in tidal disruptions of main sequence stars, it's known that a very large fraction of the gas just escapes to infinity. So what really?
Okay, so what will happen if you take a ball of gas like one of these young stars and you shred it? Basically, you overflow your Roche lobe and you completely shred it. What will happen is the gas will get spread out, and some of the gas will go flying off indeed with very high velocities, and some will be captured, basically half, right? So the question then is, when you slice your star in half, because some things will lose a little bit of energy and some will gain a little bit of energy, so they're either enormously bound or flying off with high velocities because our velocity of the orbit is very high. Now the question then is, you slice your star in half this way, okay, what happens to the core? Where does the core fall? Okay. Now, the point with the car thing is a horrible thing because it's not a nice thing to throw at car accidents. But you could forget the core in the sense that you could say, well, the core is a very dense thing. It doesn't even care about the hydrodynamics of the envelope. That's what I was trying to do with the analogy. Okay? And in that sense, like the driver doesn't care about the car stopping because he's not connected to it without the seatbelt. Just keeps going. Right? But if you are connected hydrodynamically, then you might well be in the bit that falls in, was my point. Right? You kind of sit in the middle of this thing tied to the gas that's doing this stuff.
Yeah, it's not exactly clear to me why the car stops.
Well, half of it stops, right? So the analogy with the car is bad in that. So the only point with the car was that the core is very dense and potentially wasn't connected hydrodynamically to what's going on in the core. That was the only point of that analogy, okay? But if you think about it as a ball of gas getting shredded, when a ball of gas gets shredded by a black hole, okay, what people find is that you lose half of the mass with a lot of energy, and the other half gets really captured, right? The way to think about that, perhaps, is everything's moving on orbits, right? And something goes on in the envelope, it gets spread out, and the orbits get changed a little bit, right? So if you're coming in on a parabolic encounter, and you change some of the orbits to be a little bit less velocity, then they're very bound, right? And you give these others a little bit of extra velocity, then they're very unbound, right? They have huge velocity at infinity, right? And it turns out you basically split the star in half that way. You capture half the mass.